Where did the universe come from? What did the universe look like before the Big Bang? The most widely accepted answer today is, the universe came from nothing. But what exactly does nothing mean according to scientists? Today, we will explore a relatively profound topic. After listening, your understanding of the universe might be completely overturned. First, let's define the term nothing correctly. In most people's minds, nothing means no light, no air, no sound, and no particles of any kind, almost like a quiet and pitch-black space. However, this understanding does not hold up in physics. In the framework of physics, nothing does not exist, because even the emptiest, loneliest space has never truly been silent. Physicists call this state the vacuum state. It may sound complex, but it simply means that space is never completely still. In the world of quantum mechanics, the vacuum is like a machine that is never turned off, always accompanied by tiny energy fluctuations. These energy fluctuations, known as vacuum fluctuations, happen so quickly that they cannot be directly measured, but their existence is undeniable. There is an experiment that proves this, called the Casimir effect. If you place two metal plates very close to each other, a weak attractive force will emerge between them. This force is caused by those invisible quantum fluctuations. Therefore, even the emptiest space we can create is not truly empty. Even more interestingly, physicists have identified several different types of nothingness. For example, false vacuum, which appears stable but is actually filled with uncertainty. You can think of it as a ball resting on the top of a hill. It seems stable, but with the slightest nudge, it will roll down. Some cosmologists believe that the birth of the universe might have come from such a false vacuum state. Another type is called de Sitter space, which is a solution to Einstein's general relativity equations. You can imagine it as a canvas that is already taut and curved. Though no painting has been made yet, it already possesses energy. If the Big Bang originated from de Sitter space, then the so-called nothingness actually contained the material for the universe's expansion. On a smaller scale, the Planck scale represents the smallest space scale allowed by nature. At this scale, space-time may not be smooth, but rather, like boiling liquid, filled with tiny bubbles that constantly appear and disappear. We call this state quantum foam, and it might be the most primordial form of nothingness we can describe. It is chaotic and unstable, elusive, but perhaps it is the raw material from which the universe was born. So, when scientists say that the universe came from nothing, they are not referring to the empty void we imagine. True nothingness is a vacuum filled with fluctuations, a false vacuum that could collapse at any moment, de Sitter space containing energy, or even quantum foam at the Planck scale. All of these states are active in their own ways, creating the possibilities for the birth of the universe. Here, we must mention the inflation theory. To understand why some scientists are now challenging inflation theory, you must first know why it became so popular. The Big Bang theory explains how the universe expanded from a hot and dense state, but it left several unresolved mysteries. In the early 1980s, Alan Guth and Andre Linde proposed the inflation theory, which solved these mysteries in one fell swoop. The inflation theory was not just a temporary fix, it offered a profound solution to multiple problems. The first problem was the horizon problem. In the cosmic microwave background radiation, we observe that the temperature is nearly the same in all directions. However, according to the conventional expansion rate, regions at opposite ends of the universe should never have had a chance to communicate. So, why are their temperatures so close? The explanation offered by the inflation theory is that before the universe began expanding, its scale was small enough that the entire universe could communicate and thus achieve equilibrium. The second problem is the flatness problem. Observations show that the universe's geometry is almost perfectly flat. Without some mechanism, the universe would either quickly curl up into a ball or expand too fast to form any structure. The inflation theory explains that the inflationary phase stretched space to a near-perfect flatness, much like how a small area on a balloon, no matter how round the balloon is, always looks flat. In addition, the inflation theory also explains how galaxies form. The rapid inflation stretched quantum fluctuations to cosmic scales, and these fluctuations later evolved into clumps of matter that eventually formed galaxies, stars, and all celestial bodies. The inflation theory cleverly connects the quantum world with the macroscopic universe. Due to these advantages, the inflation theory quickly became mainstream. But it is not without its flaws. The biggest challenge is that it relies on an unproven hypothesis, the inflaton particle. Moreover, there are multiple versions of the inflation theory, and each predicts slightly different outcomes, making it difficult to determine which version is correct. For decades, the inflation theory dominated, as it was more consistent with observational data. However, these questions have never ceased. Just this year, a new idea was proposed by a team of Spanish and Italian scientists, led by Raúl Jiménez from the University of Barcelona. This team raised a bold question: what if we don't need the inflaton particle at all? What if gravity and quantum mechanics alone are enough to explain the origin of the universe? Their idea is based on de Sitter space and incorporates the concept of gravitational waves. Notably, these gravitational waves do not need to be generated by black holes or supernovae. They are a natural property of spacetime itself. This means that the early universe may have been filled with these ripples from the beginning, and these waves, through their superposition and interaction, were enough to shape the initial structure of the universe. The core idea of this model is that the origin of the universe does not require any unknown physical fields. Gravity and quantum theory alone are sufficient to explain it. What is interesting about this new model is that it does not rely on any untested hypotheses. Gravitational waves and quantum mechanics are already known physical phenomena that have been confirmed by multiple experiments. Therefore, this proposal offers a new perspective, challenging the traditional inflation theory and presenting a simplified approach based on existing physics. Of course, this new theory still needs to match experimental and observational results, particularly with the observations of the cosmic microwave background radiation. This is the gold standard for testing any early universe model. If this new model can successfully explain the subtle variations in the microwave background, it could become a strong alternative to the inflation theory.